Greetings! This is the fourth lecture on the Riesz representation theorem. On the previous lecture we already stated the theorem, but let's briefly recap. Let x tau be a locally compact Hausdorff space and let lambda be a positive linear functional defined on the space of compactly supported continuous functions, namely Cc of x. Then the theorem tells us that there exists a sigma algebra F containing the Borel sets and a measure mu defined on F with the following properties. The functional lambda is represented by mu in the sense that lambda of F equals the mu integral of F for all functions f in Cc of x. Second, the measure mu has three regularity properties A, B and C. The property A states that mu assigns a finite value to compact sets. Property B states that mu is autoregular. The mu measure of any set E in the sigma algebra F can be approximated from above by the mu measures of open sets U containing E. Property C states that mu is inner regular, although only in a restricted sense. If E is a set in the sigma algebra F and has finite mu measure, or E is an arbitrary open set, then the mu measure of E can be approximated from below by the mu measures of compact sets K contained in E. As we already proved on the previous lecture, the measure mu defined on the sigma algebra F and satisfying all these properties is unique. It may be worth mentioning separately that the uniqueness of the sigma algebra F is not part of the uniqueness claim. However, if two measures on different sigma algebras F1 and F2 satisfy all the properties listed in the theorem, then the measures would agree on the intersection of these two sigma algebras. This intersection in particular contains all the Borel sets. The purpose of this lecture is to prove the existence of the sigma algebra F and the measure mu. The construction will be relatively simple, but there are so many properties to verify that the proof takes a fair amount of space and time. To save some of both, we start by introducing the following notation. If U is an open subset of X, we will say that the function f is dominated by U if f is a compactly supported continuous function whose support is contained in U and f only takes the values between 0 and 1. The domination of f by U is denoted by this wiggly inequality symbol here. Of course, such functions f will typically be produced by Urysohn's lemma. In a similar spirit, if k is a compact subset of x, we say that the function f dominates k if f is a compactly supported continuous function, f only takes values between 0 and 1, and f equals 1 on the set k. Now, if k is a compact set contained in an open set U, Urysohn's lemma states exactly that there exists a function f which dominates k and is dominated by U. We are now fully prepared to construct the measure mu and the sigma algebra F. We first define the values of mu on open sets U. If U is an open set of X, we define mu of U to equal the supremum of the values lambda f, where lambda is the given positive linear functional we are interested in, and f is any function dominated by U. Next, we define the value of mu on an arbitrary subset E of X. We define mu of E to be the infimum of the values mu of U, where U is an open set containing E. We immediately have to consider a question of consistency. If E is an open set, it looks like we have two different definitions for mu of E. It is best if you just pause the video for a moment and think yourself why the definitions agree in this case. For this reason, it is safe to use the symbol mu in both definitions. An interesting point is that the set function mu has now been defined for every subset E of X. In other words, the values of mu have been defined on the full sigma algebra P of X. However, this does not mean that mu is a measure on p of x. There is in general no chance that mu would be a countably additive set function on a sigma algebra quite this large. To make mu into a measure, we need to make the sigma algebra smaller, and this is what we will describe next. Before defining the final sigma algebra F, we define an intermediate collection of sets, which is called F0. This collection consists of all those subsets E of x whose mu measure, as defined above, is finite, and whose mu measure can be approximated from below by the mu measures of compact sets contained in E. The point here is that the inner regularity of mu is, in a sense, already baked into the definition of the sigma algebra on which mu will eventually be a measure. It is quite clear that F0 cannot generally be a sigma algebra. It only contains sets of finite measure, and this property would not survive under countable unions. To fix this issue, we finally define F as the following class of sets. F contains every subset E of x whose intersection with every compact subset K of x lies in the family F0. It will turn out that F is a sigma algebra, although this probably does not look too clear at the moment. In the next sections, we will establish that the set function mu restricted to the sigma algebra F is a measure, and it satisfies all the claims of the Riesz representation theorem. We will start by checking three simple points. The set function mu is monotone, it satisfies the outer regularity property B, and the triple xf mu is complete. You might wonder what this last statement even means before we have checked that F is a sigma algebra. But actually, the definition of completeness makes perfect sense if F is any set family. We will see this in a moment. First, let's recall the definition of mu. Mu of E equals the infimum of mu of U, where U is any open set containing E. It is rather immediate from this definition that mu is monotone. If A and B are any subsets of X, and A is contained in B, then there are simply more open subsets containing A than B. That's why the infimum for A is smaller than the infimum for B. And this shows that mu of A is no larger than mu of B as desired. Note that this argument worked for all subsets A and B of X, and not just those in F. Second, we check the outer regularity property B. This is completely trivial from the definition of mu. If E is any subset of X, the outer regularity property asked that mu of E should be the infimum of the values mu of U, where U is open and contains E. But this is precisely our definition of mu of E. Again, we see that the outer regularity holds for all subsets of X, and this had nothing to do with the sigma algebra F. Finally, let's check that the triple xf mu is complete. Unlike the previous statements, this one definitely has to do with the family F. What we need to check is that if n is an element of F with 0 mu measure, and A is any subset of n, then A is also a member of F. Recall that the membership of A in F meant that the intersection of A with every compact set should be an element of F0. Next, let's scroll back here to recall the definition of F0. This was the family of all sets with finite mu measure, whose measure can be approximated from below by compact sets. It is clear that F0 contains every set with 0 mu measure. Namely, in this case the approximating compact subset can simply be chosen to be the empty set. Now let's scroll back down. We are claiming that if A is a subset of the null set n, then A is also an element of F. But now it's clear by monotonicity that A is also a null set, and also the intersection of A with every compact set is a null set. Hence, these intersections of A and K lie in F0, and this means that A itself lies in F. This completes the proof of the completeness of XF mu. The next task will be to prove that the set function mu is countably subadditive on the full sigma algebra P of x. In other words, if A1, A2 and so on is a countable sequence of arbitrary subsets of x, then the mu measure of the union is no larger than the sum of the mu measures. We start by verifying this in a very special case, where we only have two of the sets and both of them are open. Let U1 and U2 be open sets. We claim that the mu measure of their union is no larger than the sum of their mu measures. Here is a reminder of how mu was defined on a generic open set U. Mu of U is the supremum of the numbers lambda of f, where f is dominated by U. With this definition in mind, we need to do the following. We need to fix an arbitrary function f, which is dominated by the union of U1 and U2, and show that lambda of f is bounded from above by the sum of mu U1 and mu U2. Here is the first time when partitions of unity will appear. Let K be the compact support of the function f, so K is contained in the union of U1 and U2. By the partition of unity theorem 2.12 from the previous lectures, we can find two functions h1 and h2, where h1 is dominated by U1, h2 is dominated by U2, and the sum of h1 and h2 equals 1 on the set K. This last property implies that f can be written as the sum of f times h1 and f times h2. Now we may estimate as follows. First, by the linearity of lambda, lambda of f equals lambda of f times h1 plus lambda of f times h2. Then note that the function f times hj is dominated by uj. Therefore, by the definition of the mu measures of open sets, like uj, the previous sum is bounded from above by mu u1 plus mu u2. And this is what we claimed, and now we have shown that the mu measure of u1 union u2 is no larger than mu u1 plus mu u2. Using the very same argument, or applying induction instead, the previous inequality could be generalized to any finite number of open sets u1, u2 through to un. The mu measure of their union is bounded from above by the sum of their mu measures. Now we are prepared to treat general sets aj, and indeed a countable number of them. Let a1, a2 and so on be arbitrary subsets of x. For every index I, choose an open set ui which contains ai and has mu measure no larger than the mu measure of ai plus epsilon over 2 to the power I. Here epsilon is any given positive number. Now we define U to be the union of the sets ui. Then U contains the union of the sets ai, and the monotonicity of the set function mu implies that the mu measure of the union of the sets ai is bounded from above by the mu measure of U. We claim that the mu measure of U is further bounded from above by the sum of the mu measures of the sets ai plus epsilon. Chaining these two inequalities together and letting finally epsilon tend to 0 in the end, this will complete the proof of the subadditivity. Fix a function f dominated by u. Then the support K of f is compact and the sets uj form an open cover of K. So K is already covered by some finite number of the sets uj, say u1 through to un. This means that f is dominated by the union of the sets u1 through to un. It follows from the definition of mu that lambda of f is bounded from above by the mu measure of this finite union. Now we are in a position where we may use the first part of the argument for finite unions of open sets. This mu measure is bounded from above by the sum of the mu measures of the sets uj. Finally, the sets uj were chosen so that the mu measure of uj is bounded from above by the mu measure of aj plus epsilon over 2 to the power j. Since the function f dominated by u was arbitrary, the previous inequality shows that the mu measure of u is indeed bounded by a sum of the mu measures of the sets aj plus epsilon. And this is what we claimed, and the proof of the subadditivity of the measure mu is complete. Let's quickly summarize what we have shown so far. We have shown that mu defined on the full sigma algebra P of x is a monotone, countably subadditive set function. It is also clear that mu assigns the value 0 to the empty set, simply because the empty set is open and the only function which it can dominate is the 0 function. Of course, lambda of 0 equals 0 by linearity. These properties of mu mean, in common terminology, that mu is an outer measure. In addition, we already know that the property B holds, that is, the mu measures of arbitrary sets can be approximated from above by the mu measures of open sets. Our next goal is to establish the property A, which said that mu assigns a finite value to every compact set. While doing this, we will also see that the set family F0 contains all the compact sets, but more on this in a moment. We will actually prove something rather precise. If K is a compact set, we will show that its mu measure can be expressed as the infimum of the values of the functional lambda at f, where f is a function dominating K. There really are such functions f by Urysohn's lemma, so in particular the mu measure of K will be finite. Of course, this formula for compact sets is a close relative of the formula for open sets, which we took as the definition of mu. We then start the proof of the formula, and we first prove that mu of K is bounded from above by the infimum on the right hand side. For this purpose, fix an arbitrary function f which dominates K. In other words, f is continuous and compactly supported, only takes values between 0 and 1, and exceeds the characteristic function of K. We claim that mu of K is bounded from above by lambda of f. To show this, we fix a parameter s between 0 and 1. You should think that s is very close to 1, and eventually we will let s tend to 1. Now we let us be the set of points in X where f is strictly bigger than the parameter s. Note that us is an open set by the continuity of f. Since f equals 1 on the set K, we moreover see that K is a subset of us. We also note that if g is any function dominated by us, then g is bounded from above by the characteristic function of us by definition, and this is further bounded by 1 over s times f by the definition of us. These two observations allow us to make the following estimates. First, the mu measure of K is bounded from above by the mu measure of us by monotonicity. Second, by definition, this quantity is the supremum of the values of lambda g, where g is dominated by us. Then, every number inside the supremum is bounded from above by the inverse of s times lambda f. Once we let s tend to 1, we can now conclude that the mu measure of K is bounded from above by lambda f, as we claimed. One step in the previous argument was actually less trivial than it might appear. We used the fact that if f and g are functions in cc of x, with g bounded from above by f. Then also lambda of g is bounded from above by lambda of f. And this is the spot in the proof where the positivity of lambda gets used. The stated inequality between lambda g and lambda f follows immediately from the linearity and positivity of lambda when applied to the function f minus g. Let's then resume the proof of the equation for compact sets K we claimed earlier. It remains to show that the infimum of the numbers lambda f, where K is dominated by f, is bounded from above by mu of K. To show this, recall what mu of K even means. By its definition, we may choose an open set U containing K, whose mu measure is no larger than mu of K plus epsilon. Here epsilon is an arbitrary positive number. By Urysohn's lemma, we may now find a function f which dominates K and is dominated by the set U. Then lambda of f is bounded from above by mu of U. This was further bounded by mu of K plus epsilon by the choice of U. Since epsilon was arbitrary, we have now shown what we claimed. We have shown that the mu measure of K equals the infimum of the numbers lambda f, where f is the dominating function for K. We close this section by pointing out that the family F0 contains the compact sets. We had better recall the definition. F0 consisted of all those subsets E of x which have finite mu measure and whose mu measure can be approximated from below by the mu measures of compact sets. Of course, the approximation from below is trivial if E itself is compact. So the only requirement in this case is that mu of E is finite. But this is what we just established. So we conclude that F0 indeed contains the compact sets. The key remaining points of the proof will be the inner regularity of the measure mu, the proof that mu is really a measure on the sigma algebra F, and then perhaps the most interesting point of all, namely that mu actually represents the given functional lambda. Not to make the videos too long, we stop here and continue with these remaining points on the next lecture. Goodbye for now.